Today I'll be presenting about task dependency graphs in parallel and distributed computing. Task dependency graphs, often modelled as DAGs, are foundational for understanding how complex computational tasks can be efficiently executed across multiple processors or distributed systems. What is a task dependency graph? A task dependency graph is a directed acyclic graph, or DAG, where each node represents a computational task and each edge represents a dependency. This means a task cannot start until all tasks pointing to it have completed. These graphs serve as the backbone of efficient scheduling in parallel and distributed computing. Why task graphs are important. Task graphs matter because they reveal how much of a program can be parallelized. They help us identify parallel sections of code, find the critical path, reduce total execution time, improve processor assignment in distributed environments. In short, task graphs help us maximize performance. Let us look at this task dependency graph, which demonstrates how a computation is broken down into smaller subtasks. At the bottom level, we begin with 4 independent operations: min 2312, min 930, min 3727, and min 817. Each of these tasks calculates the minimum of 2 numbers. The results of these computations now move to the next level. The outputs of min 2312 and min 930 combine to form a new task, min 129. Similarly, the outputs of min 3727 and min 817 combine to form another task, min 278. Once these 2 intermediate results, namely 9 and 8, they feed into the final computation at the top of the graph. The root task performs min 9, 8, and the final result is 8. This illustrates how a larger operation is decomposed into multiple parallel tasks, each performing a small portion of the work. These intermediate results propagate upward until the final answer is produced. It shows dependencies between tasks and highlights the opportunities for parallel execution. Here we have a simple task dependency flowchart that represents how tasks need to be executed in order. At the top, we start with task A. This is the initial task, and nothing can begin until task A is completed. Once task A finishes, the workflow splits into 2 parallel branches. One branch goes to task B. The other branch goes to task C. This means tasks B and C can run simultaneously because they are independent of each other. After tasks B and C are completed, they both feed into task D. Task D depends on the output of both B and C, so it can only start once both tasks are done. Finally, task D leads to task E, which is the last task in the sequence. Task E cannot start until D finishes, making D part of the critical path. This flowchart clearly shows which tasks can be done in parallel and which ones must wait for others to finish. It helps us visualize the structure of execution in parallel and distributed computing systems. Critical path analysis script. The critical path is the longest chain of dependent tasks. This path determines the minimum possible execution time, even if we had unlimited processors. In this example, the critical path is A, arrow C, arrow D, arrow E. Any delays along the critical path increase the total runtime. Parallelism in task graphs. Parallelism describes how many tasks can run at the same time. In our example, B and C can execute simultaneously. The more independent tasks we have, the greater the potential speed-up. Thus, DAGs help us see where parallel execution is possible. Scheduling strategies. To execute a DAG on multiple processors, we use scheduling algorithms. Some common strategies include list scheduling, a simple, greedy method. Critical path first, which prioritizes tasks on the longest path. HEFT, widely used in heterogeneous distributed systems. Work stealing, used in Silk and Java's fork/join framework. These methods aim to distribute the workload efficiently and reduce total execution time. Real-world applications. Task dependency graphs are used everywhere today. Apache Spark uses DAGs for RDD transformations. Airflow and Argo use them to orchestrate workflows. Scientific computing uses them in simulation pipelines. GPUs like CUDA use task graphs for optimizing kernel execution. Summary. To summarize, task dependency graphs model the relationships between computational tasks. They help identify parallelism and execution bottlenecks. They guide scheduling in parallel and distributed environments. And they are widely used in real-world systems like Spark, Airflow, CUDA, and HPC frameworks. Understanding DAGs is essential for efficient system design and high-performance computing.